Okay, so I think I'll get started. So first about the midterm. So the midterm is graded and grades are posted. I think the average is about like 85 or 84. So overall, I think it is very good. So I think question two, yeah, question two is a little bit hard, but I think most of you still make very good progress on that question, and some of you even got it completely correct. So which is very good. So yeah, so any questions about midterm one? Okay, yeah, if you want to talk about your midterm one with me, you can feel free to come to my office hour or make appointment with me. Okay, so now I think I want to
the exam, well, pretty much the next one of the following exams, are they going to be as theoretical, or is it going to be more applied?
as theoretical or as more applied. I think pretty much. Yeah, I think that depends on what we will cover. So I think for the next exam, yeah, so I think gonna be pretty much similar to the first exam, because I don't think it's possible to test like your R skills or or something like that during exam. So we need to have something that can be written down. So I think, yeah, it should be pretty much similar. So for the theoretical part, I might ask you to derive some properties. And for the applied part, I think pretty much similar to midterm one. So I will ask you to maybe read the plots and discuss it. I think that's pretty much the midterm two would be like. Yeah, but I think you guys are all did a very good job on the first one, so which I think is very good. Okay, so okay, so now let's get back to, yeah, and as I said, if you have more questions or other things that you want to discuss with me, just feel free to let me know or just make an appointment with me. Okay, so now let's get back to what we left in last class. So in last class, we talked about like the properties that when the ARP process is stationary. And so why we want to care, so why we want the ARP to be stationary. The reason is that for a stationary process, the stationary process can always have a word decomposition. And the word decomposition says that we can use the previous information to predict the current information. Okay, so that is, we can use the previous white noise to predict the current outcome X. And this concept is sometimes called causal. So which is a very important concept in the ARMA model. So now let me write down the formal definition of causal, okay, and discuss it a little bit. Okay, so a time series xt is said to be causal if it can be written as following. So xt equal to mu t plus an infinite sum of the white noise, where each white noise is weighted by the coefficient psi j. So mut is some, so the first part mut is some like constant and plus some white noise. I mean, a linear combination of the white noise.
How would you, if you were able to write it in terms of white noise, how would you go about seeing whether those coefficients converge or not?
Yes, that's a very good question. We will talk about today. So actually to find each psi j is not that easy. Actually, it's quite complicated. We have some special case. So for example, if it is like a AR1 process, and we know that each psi j is equal to phi to the power j, okay? But for maybe AR2 or AR3 or even ARP, to find each psi j is not that easy. But the lucky thing is that we can ask R to help us to find all this. So I think I can go to that part. Yes, so I think I can go to that part today.
Are the size unique?
Are the size unique? Yes, so that's a very good question. I think the psi j is unique, but the psi j is unique. Let me think for 1 second. The psi j is unique. Psi j unique. Yes, I think so. Yes, the decomposition gonna be unique. We will talk about like one thing that is not unique today. Maybe two things that is not unique today. One is called parameter redundancy, and the other is the uniqueness of the invertible model. So it's not quite related to what you just asked, but yeah, it's not that similar to what you just asked. But yeah, I think psi j have to be unique. Yes, so if your model is correctly specified, then this psi j gonna be unique. Yes, I think that's the answer. Yeah, so you have to have a correctly specified model, then your psi j is unique. Yeah, so what I mean by correctly specified. So, for example, like your AR model, say like your XT is actually AR2, but if you specify it as an AR4 or AR5, then the psi j gonna be different. But if your model is correctly specified, if you correctly specified as AR2 model, then the psi j gonna be unique. Yes, I think that's right. Okay. Okay, so that's causal. And you can see the nice thing about the causal is that everything that we use to explain X is what happened before. Okay, so we use the previous information to predict the current XT. So which is very nice. Okay, and you can see that I mean, this is like a corollary. Corollary is that any stationary process has a causal representation. Okay, and in our case for specific, we are interested in the ARP model. Okay. And we studied like in what situations this ARP model is stationary. The result is that all the roots of like that polynomial, if it is within the unit, if it is within the unit circle, then it is a stationary process. Okay. So very good. So now we have discussed like AR model, and now let's talk about the MA part of the AR-MA model. Okay, so let's look at the MAQ model. So the MAQ model can be written in this way: WT plus theta 1 WT minus 1 theta 2 WT minus 2. T minus Q. Okay. And all this W are again white noises. Okay. So couple of like remarks here. So the MAQ is stationary. So which is very good. So it does not need any requirements to make it stationary as an ARP model. It's automatically stationary. So for example, for a A1 process, P equal to WT plus theta WT minus 1. Okay. So in this MA1 process, you can check the expectation of XT is just equal to 0. And I will not show the steps here, but you can check the autocovariance function for a MA1 process is independent of time. I will write the autocovariance function for later reference. Okay. So you can easily see that everything here is independent of time. So which suggests that this MA1 process is a stationary process. Okay. So which is very good. And we know that since this is a stationary process, and we know that it always have a causal representation. And the causal representation here is very simple, actually. Psi j is equal to the causal representation of the MAQ model is very easy, very straightforward. So it's the psi j, the causal part is equal to theta j if j is less than q, which is less than the order of the MA model. And it is equal to 0 if it is larger than the order of the MA model. Okay. Okay, so I will first finish this MA model, the very important concept of this MA model. Then I'll move to the R to show you some AR and MA model in R. Okay. All right, so this is MA model. Let me see. Actually, this MA model is sometimes not unique. Okay, so what I mean unique here. So let's just see an example. Okay, so let's just consider an MA1 model. The first MA model is xt equal to wt plus 1/5 wt minus 1. And let's assume this wt is an IID process with mean 0 and variance 25. Okay. And then let's have another MA1 process called YT. And this YT is equal to VT plus 5 VT minus 1. And this VT also follows an IID process with mean 0, variance 1. Okay. Unfortunately, you can show xt and yt share the same autocovariance function. Okay. Or that's a thing from the textbook. So it's 2650. Okay. So you can show that xt and yt actually share the same autocovariance function, and of course the autocorrelation function. So which is not good, right? Because the reason is that we only observe xt and yt. We do not observe wt or vt. So which model we should pick? Okay, we basically have like two wt and vt, two white noise process that can generate the same MA process. So which is not good actually. So we do not observe wt or yt. So which model to pick? Right. So that's a question. The intuition here is that we will try to mimic the AR models and choose a model that can have an infinite AR representation. Okay. Solution. Okay. Yeah, so a model that with this infinite AR representation would have like much nicer properties compared to the other models, okay, because we can always write it as an infinite sum of like all the white noises. Okay, so now let's back to our example and see like which model can have this infinite AR process. Okay, so we have now two models. Okay, so let's get back. So this is our MA process, wt plus theta, wt minus 1. And if we move wt to the left-hand side and move xt to the right-hand side, oh no, just I mean, this is equal to this, not move. Okay, so this is what we have. So wt is equal to xt minus theta, wt minus 1. Okay, so you can see this is somewhat like the AR process, right? The difference is that this wt and wt minus 1 are the white noises. Okay, but it has like this AR1 representation. Okay. And from our AR1 representation, we know that if this theta 1 is I mean, if this theta, the absolute value of this theta is less than 1, then WT gonna be equal to then we know this WT gonna be a infinite representation of XT minus J. So just think of like here, the XT as the white noise, okay, in the AR1 representation. So now we can see this has an infinite AR representation. Okay.
And that's just through Wold, huh?
Question?
That's just through Wold, huh?
Yes, that's through the word decomposition, and that's a special case, a very nice case of the word decomposition. So if it's an AR1 model, then the word decomposition, like each coefficient of the word decomposition is the coefficient to the power J. Okay, so what does this mean in our example? So in our example, we will pick, I think, xt. Okay, we will pick xt equal to wt plus 1/5 wt minus 1, right? Because 1/5 is less than 1. Okay, so we'll pick the first model. The model that with the coefficient 1/5, and the white noises follow a normal distribution with mean 0 and variance 25. Right, so that's it. And a little bit more discussion on this. So that's just an aside. It's not that important, but I just want to present for your reference. So you might be wondering that why we only have like 2 solutions. I mean, why we only have like 2 models that would generate a same MA1 process, and why there's always one that would satisfy like this AR, infinite AR representation. That's a pretty high level thing, but I think it's important, especially like talking about like in this MA1 process, it's not that hard. If you're talking about like MA2, MA3, it's gonna be complicated. So why only 2 solutions that would generate the same model? And why only one of them work? Right, to show this, it's actually like, especially in this case, it's not that hard. So we can show that the autocorrelation function is equal to this. Yeah, just using the result that I give you, the autocorrelation function, just using that result. I give you in page number 3. And if you solve this, this is actually a function with unknown theta and theta, just a quadratic function. Okay, and for a quadratic function, you know that there will be 2 solutions. So that basically answers our first question. There will be always 2 solutions. And actually it can be shown. There's only one theta such that the absolute value of theta is less than 1. Okay. Yeah, so for this case, it's not that hard to show, but I mean, if you move to a MA2 process, then it will probably not be a quadratic function, it might be a cubic function. Yeah, to show the root of the cubic function, it's not that easy. Okay, yeah, but always you can definitely do that. So that's just an aside. So we will always, like for our case, we will always have a solution, and that solution would satisfy the requirement, the theta, the absolute value of theta is strictly less than 1. Okay. And in time series, we have a very nice definition on this situation. Okay, and we call this invertible. So a time series is invertible if it can be written as an infinite sum of the AR representation. Okay, and also again for constant pi j, and the summation of pi j square gonna be finite. Two remarks I want to make here. One, you can see again that WT now only depend on previous xt minus j, which is very good if you want to do prediction, because xt minus j is observed. Okay, and we know that WT only depends on the previous value of xt minus j. So that means at time period t, you can use all your previous information to predict the current value of the white noise WT. Okay, and number 2. This is somewhat by definition. So the MAQ becomes a AR infinity model. So why this is the case? It's easy to understand, because that we know each WT now can be represented as an infinite AR process. So the summation of them have to be an infinite sum of AR process. Okay, so WT minus 1 to theta Q, WT minus Q. So this is AR infinity, also AR infinity. Okay, so that means their summation have to also be a AR infinity. Okay, so any questions here?
Actually, is so.
Yeah.
The point of all this is to predict white noise in your time period.
Yes.
Okay.
Yeah. That's a, yeah, right, yes. Yeah, but it still has like in applications, it still has a lot of trouble. I mean, a lot of problems because you do not have like, basically you do not have infinite time amount of data. So, but however, if you know that this pi j, this like coefficient would like diminish at infinity, then you can just use a finite periods of data to do the prediction and assume like the rest of the AR process does not like, I mean, or theoretically say that it will converge in probability to 0. Yeah, but you still have a lot to show, but here is just a very nice, clean math representation here. Okay, so if there's no questions, so I want to give you some examples of the AR and MA process in R. And after that, we will move to the AR-MA process. Okay, so now let me switch back. Oops. Here. So let's draw this. We have like the library. So the first example is a AR example. So we do 2 plots. Let's minimize this. Okay, let's do 2 plots. The first plot is that it's called like the command I use here is called like the arima.sim. So it's the arima simulation. And the order is that we will do so the arima has like 3 components here. One is AR, the first is AR, the second is I, the third is MA. Okay, and here we are doing a AR1 model. Okay, so that means the order here is 1, 0, 0. Okay, and the AR, the coefficient of the AR we choose here is 0.9. Okay, and for the second plot, the coefficient we choose is negative 0.9. Okay, so the first is the AR process with coefficient 0.9. The second is the AR coefficient, AR1 process with coefficient negative 0.9. Okay, and if you want to do, say, like the simulation of the MA, or you want to also include the integrated part, you can basically change like the 0 and 0 here. Okay, so we will talk. We talk like MA already, but we haven't talked about like the integrated model. But we will talk that once we finish the AR-MA model. Okay, so here's the output. So the first plot, or the top plot, is the AR1 with coefficient positive 0.9, and the second plot is with the coefficient negative 0.9. So you can see it's very different, these 2 plots. Okay, so all we change is to change this positive sign to this negative sign, but we actually got a very, very different plot. And this, so the second plot is actually much choppy than the first plot, and this makes a lot of sense. The reason is that we choose like 0.9, right? So that means the second period is positively related to the first period. So that means if your first period's observation is a positive number, then it is highly likely that your second period observation is also a positive number. Okay. But here it becomes like the bottom plot, it becomes different. So if your first observation is a positive number, and if you times it by negative 0.9, and plus some like white noise, it is highly likely that the second period observation is negative. So the sign of the second period gonna be different from the first period. So that's why you're seeing like this up and down, like plots in the second plot, in the bottom plot. However, like in the top plot, the next period observation is likely to have the same sign as the previous observation. So that's, we will see a much smooth like plot. Okay. All right, so that's the AR1 process. And here I think I do the AR2 process. The AR2 process. This is the AR2 process. So you can see all I changed here is that I changed the order from 1 to 2 because now I want to do an AR2 process. And the integrated part is 0. The MA part is also 0. And the coefficient for the AR part is 1.5 and negative 0.75. Okay. And here's a plot. Okay. And back to, I think, back to Gabe's question. So we know that for any stationary AR process, we can always write as a infinite representation of the MA process. So, but I said like the coefficient to obtain the coefficient is actually not that easy, but luckily the R can help us to do this. And the code for that is the ARMA to MA command. Okay, so what you do, I think, is that you, so this is our first model. So the AR is 0.9, and we want to give it, yeah, I run this before already. So yeah, so I want to see the first 50 coefficients of the MA process if I switch this AR process to the M process. Okay, and you can see the first is obviously 0.9. The second is 0.9 squared, which is 0.81. The second is 0.9 to the power 3. The fourth is the 0.9 to the power 4th. Okay, and you can see as the time period increase, the coefficient shrinks to 0. Okay. Yeah. So for this AR1 process, we have like this very good result. The psi j is equal to the theta to the power j. But for a arbitrary AR process, it's not possible to have this closed form results of the MA infinitive process. But we can still ask the computer to solve this for us. So in this part, I just do the ARMA to MA, where I consider a AR2 model, and this AR2 model is coefficient 1.5 and negative 0.75. Okay, and the psi we got is this. Okay, yeah, which is the good things that you can see it also converges to 0 as time increases.
And these are
yeah, this zeros, I don't know why, but I definitely think you can show this. I do not 100% sure why there's a 0, but yeah, that might be interesting to see why there's 0 here. Yeah, but the idea is that the software will help us to do this. So what this do is to ARMA to MA, and this is plot AR2, and this is plot AR1. Okay. Yeah. Yeah, so I think at this point you should be very familiar like with all this R commands. It's pretty straightforward, I think. Okay, so now let's look at a MA model. Okay. So the MA model we consider here is that, say, like what I changed here is that I changed the order to 0, 0, 1, because I consider a MA1 model. So the AR part is 0, the integrated part is 0, and the MA part is 1. And the coefficient for the MA, we consider 0.9 and negative 0.9. Okay, so we plot the 0.9 in the top plot and the negative 0.9 in the negative plot. Yeah, and again, you will see that the negative 0.9 is much choppier than the positive 0.9. And the reason is basically the same as the AR process. Okay, so if you write this MA process to I think to the AR, if you write this AR process to, sorry, if you write this MA process to the AR representation, and you will see that this positive 0.9 will make you like the second period to be more correlated with, to be more positively correlated with the first period. And if you choose this theta to be negative 0.9, then the second period is more likely to be negatively related to the first period. So that's why you got a smoother plot and a choppy plot. Okay. So this is plot MA1. So any questions here?
Could you possibly go back over what the arima.sim list order with the first value, second value, and third value pertains to?
Yes. So the arima.sim is to simulate a ARIMA model. And we put a list here. And this list contains a couple of things. The first is the order. Okay. So the order, the first number in the order is the order of the AR part. Okay. So for example, here, we are considering an AR1 model, so we put 1 here. And here, if we consider AR2 model, we put a 2 here, okay? And the second part in this order is the integrated part, okay? So we haven't talked about the integrated part, so for now, let's just keep it as 0, okay? And the last part of this order is the MA part, the order of the MA. So for the AR1 model, there's no MA, so we just put MA equal to 0. Okay. So in contrast, in this MA1 process, we consider the order of the MA equal to 1. Okay, so then we put 1 here. Okay, so the first part, so the order in this list determines the order of the ARIMA model you consider. And the second part of this, I mean, not the second part, maybe the, yeah, so I think this is, let me see. Yeah, right. Yeah, and once you write the order, then you need to give the coefficients of the order you specify. Okay, so if you specify a AR model, then you should tell the computer the coefficient of your AR model. So for example, here we consider the coefficient to be 0.9. So we just write AR equals 0.9. And if we want to consider a sequence, I mean, it's not sequence. If we want to consider an AR2 process, then we will just write AR equal to a sequence. And this sequence is so this first coefficient is the order 1 of your AR2 process, and the second coefficient is order 2 of your coefficient. So let me go back to, it does not show this. Okay. Yeah, so this is basically like xt equal to 1.5 xt minus 1 minus negative minus 0.75 xt minus 2. Okay, so in this part, you specify the coefficients of the AR. And if you do a MA model, then you just specify the coefficients of the MA. And if you do a AR-MA model, you need to specify AR and MA simultaneously. Okay, so you would have like something like AR equal to 0.9 here. But let me just write another one. Let's do this. Okay. Yeah. Okay. This is ARMA 11. Okay. And this n equal to 100 means that you generate the observations to 100. You can change it to 200. Let's just do it to 200. Okay. And this is let's run this. Okay. Yeah, and this is like the ARMA11 model. Yeah, ARMA11 model with 200 observations.
So what's the point of simulating these?
Simulating is right. Simulating, yeah, good question. So simulating, like in econometrics and also in statistics, we want to do a lot of simulation. The simulation is that you know the true data generating process, right? So for example, you know the data generating process is a ARMA11 process, and the coefficient is 0.9. Okay, but like in the generating process, you always have some randomness, right? You always have like this white noise part. So that white noise part will make like this plot like not always exactly the same. Okay, so this data generating process, I mean, this simulation process, if you do it a bunch of times, then you will see that whether your model, I mean, in this case, you will check like whether your model is a stable or not stable. If you like just run this graph, okay, you can see like this is ARMA11, but if I run it one more time, it's going to be different, and actually very different, right? And suppose that you do it a bunch of times, say like 10,000 times or 1 million times. Will you get a stable plot? That might be the question. Okay, so that's why you want to do the simulation.
And then it would then be kind of like almost like confidence intervals to see if you actually have identified yours correctly, to see if yours is in that stable whatever.
Exactly. That's actually called like the bootstrapping. If you heard about that, if you can use the bootstrap to construct the confidence interval. Exactly. That's correct.
Okay, thank you.
You use a simulation to check, like, I mean, in theory, you can say that, like you will have an idea of like what this ARMA11 plot would be like. But in data, or in real applications, there are always some randomness there, okay? And you will use the simulation to check whether your model is correct. So that's why you use simulation. And yeah, so that's one use of simulation, but there are also some other uses of simulation. Okay. The main idea is that the simulation would help you to check whether your underlying model is correct or not correct. Okay. Yeah. Also, I think this is a good point. So when you like run all this code on your laptop, you would get very different plot as my plot. See, if I just change it, like rerun this, let's just rerun this again, you'll get another very different plot. Yeah, and to solve this is that you can set seed. This year, 2021, okay? And if you set say 2021, that would like fix the data generating process. Then you would always get the same plot. Okay. I think, yeah, right. If you set the seed like the data generating process, because the computer does a fake data generating process, a random number generating process. And if you fix that number, say here like 2021, then it will always give you the same plot. Okay. So at home, if you got different plot as mine, don't worry, that's you are doing the correct thing, just because that your computer and my computer has different random number generating process. Okay. All right, so any more questions? one time at the beginning, or do you need to set it before each block? I think, yeah, let me think. Yeah, I'm not exactly sure, but I think if I use set seed at beginning, yeah, I never try this. I guess it's gonna be used at the beginning would be fine, I think. But you can try it yourself, maybe. Yeah. Yeah. Okay, so any more questions? Yeah. Yeah, thank you. And also let me know when you find out. It might also be different from each software to each software. So R might be different from Stata, or maybe different from Python. I'm not exactly sure. Okay, so if there are no more questions, I think I will switch back to the whiteboard and talk about our main model, which is ARMA model. Okay. So let me, oh, I think yeah, okay, great. So page 5. Okay. ARMA model. So ARMA model is, by name, you can tell it's just the combination of the AR model and the MA model. And let me write down the formal definition of the AR model, the ARMA model. The definition. A time series xt is ARMA. So the P is for the AR part and the Q is for the MA part. Okay. If let's have 3 conditions here. Number 1, xt is equal to alpha. So alpha is a constant, which I will explain a little bit later. Plus, I think this is phi x, phi1 xt minus 1. Plus wt plus theta 1 wt minus 1 theta q wt minus q. Where all these coefficients are not equal to 0. And wt is a white noise with mean 0 and variance sigma w squared. Okay. And number 2, xt is causal. Number 3, xt is invertible. So this is a formal definition of the ARMA model. It consists of 3 components. Number 1 is its setup. So the setup is easy, but it's straightforward. Just having like this ARMA setup does not necessarily mean this is an ARMA model. We also want this ARMA model to be causal and invertible. Okay, this causal is also very related to the definition stationary, but stationary is stronger than causal, right? Yes, it's stronger than causal. So any stationary process is causal, but the converse is not true, I think. Any causal model is not necessarily stationary. Okay, so this is a weak condition. Yeah, and some people or some textbook like to use causal and stationary interchangeably, but I think that's not a good practice, because I think causal and stationary, even though they are very related, and especially in this AR process, they are very related, but they are not exactly the same. They have some difference. Okay, so that's a definition. And now I want to make some remarks. Number one, let's talk about like this alpha, so which is this constant term, okay? So if the expectation of xt is equal to mu for all t, so it's like a constant mean stuff, okay? Then you will see that I just take like the expectation on both sides of this AR process, okay? So that's gonna be so all the y noises are 0, okay? So that means mu is equal to alpha plus theta 1 plus theta 2 plus theta p mu, okay? And this can be solved that alpha is equal to mu 1 minus theta 1 minus theta 2 minus theta p. Okay. Right. So that means you can actually solve alpha if you know that your xt has constant mean. Okay. And moreover, if mu is equal to 0, alpha is equal to 0. Okay. So this further means, I mean, this is also a practice or a trick. So if you demean your data, then mu is 0 and alpha is 0. Okay. If you do not demean your data, then mu is not equal to 0 and alpha is also not equal to 0. Okay, so in other words, in your regression or in your application, if you do not demean your data in the first hand, you always want to include a constant term in your regression. Okay, because in that case, mu is not equal to 0, and the constant part alpha in your model is also not equal to 0. Okay. However, if you demean your model, you can run a regression without the constant. And if you still include the constant in your regression, then the constant is gonna be 0. And that 0 is indifferent, significantly indifferent from 0. Okay, so that's a trick or something. Yeah. So in your application, if you do not demean, just run the model. You have to include the constant in your model. Okay, so that's remark number 1. Number 2, let's talk about the causal and invertible. Okay, so causal. Let's talk about the causal first. Okay, so in this model, we have 2 parts, right? The AR part and the MA part. Okay. So for the AR part to be causal, what we need. So we talk about a case that the AR part is causal, that is, it is stationary. So if this AR part is stationary, then it is always, then it should be causal. And what required to make this AR process to be stationary, we know that the roots of the polynomial gonna be within unit. Okay, so the AR part causal, we need yes. Okay. So we need this. So this is our requirement. We need to check this. And for the MA part, we know that this MA part is always causal, which is good. So to check the causal part, all we need to check is the AR part. And to check the AR part, all we need to check is whether the unit roots, whether the roots are within the unit circle or not. Okay. Similarly, let's do invertible. So the AR part is always invertible, because we know that this AOI is definitely an infinite AR process, and can always have an infinite AR representation. Okay, so which is good. And all we need to check is the MA part. So for the MA part to be invertible, I did not talk about this earlier, but it's basically the same. Okay, so we need this, the roots of this. So we change the coefficient. Okay. Okay. So we need the roots of this polynomial is within the unit circle, and the roots of this polynomial and this polynomial, we change the coefficients. Okay, so this theta are the coefficients of your MA part, and this phi are the coefficients of your AR part.
Why is this one plus and the other one's minus?
Why this? Yes, the the reason is that just if you do the math, it is just this. Let me see if I can explain this in a better way. Let's see. Let me see. I have something here. Yes, so right, because the the reason is that Right, because the reason is this, I just write it down, you do not need to know this. You see that this xt is right, this, right? Xt equal to alpha theta 1 xt minus 1 theta plus theta 1 wt. So for the AR process, what you consider is xt minus, say, theta 1 xt minus 1 plus theta t xt minus 2, right? So this comes the minus sign here. And but for the MA process, it's just xt equal to wt. So these are the positive sign here. This is a very just like the first step. And from like what I just wrote here, so you need this equal to 0. And from what I wrote here, you can set up like this polynomials, and those polynomials would like carry this signs of the phi and theta. Okay. That's actually not that important, but it's might be worth asking. Okay, so that's causal and invertible. Yeah, and we can check that. Okay, and yeah, you can check that, and you need the model to be causal and invertible. So the third comment I want to make here is, I think, a very important topic. Is called the parameter redundancy. I might do not have enough time to finish this, but I want to give you. Yeah, if I do not have time, I will talk about it next class. So this is a parameter redundancy. This is actually a very important topic in like in your analysis, because there are actually a lot of models that would give you the same representation. Okay, and actually only one of them is correct. Okay, so let's see what is like called the parameter redundancy. Okay. So let's first write this ARP using backshifter. It's just like make things easier to see, but it's not that important. Okay. So just remember this B is like the backshift. Okay. So this is your ARP model. Okay. And this can be actually written as, let's like have a big phi B. So this is your ARP model. You can also write this MAQ using backshifter. So the MAQ model is like this: 1 plus theta 1 B plus theta 2 B squared plus theta Q B Q plus WT. Okay, and this suggests that XT is equal to theta. So I just call this part phi B and this part theta B. Okay. So this implies the ARMA PQ model can be written as phi B XT equal to alpha plus theta B WT. Yeah, this just like makes things easier to read. Okay, so it's this, yeah, nothing fancy here. It just makes things easier. Okay. The problem comes here. How about I multiply both sides by some other backshifters? Let's say it's called like eta b. Okay, so you can see eta b, bb. I think let's just ignore alpha at this point. It just makes things a little bit easy. But if you have an alpha, the constant is totally fine. No need to worry about that. Okay. So you would have this model. So basically you have a new model, but the dynamics of this new model is basically exactly the same as your old model, right? So this creates problem. Two models. Two models have exactly the same dynamics, right? Yeah, and this is actually a very, I don't know, a very typical problem in most statistical analysis and also econometrics analysis. So you can always have like multiple models that would generate the same distributions of the observables. Okay, so this is what we sometimes call like the observationally equivalent. So you will have like different models that are observationally equivalent because they generate the same distributions of your observed data. And in statistics and also in econometrics, one way to address this is that we impose some normalizations. Okay. And one very standard normalization you might see in your econometrics class is that suppose you have this model y equal to beta 1 plus beta 2 x plus e. And you assume the expectation of e given x is equal to 0. This is actually a normalization assumption. Okay. So this assumption would like fix your beta 1. If you change like your expectation of x equal to 0.5, okay, then your new beta 1, like beta 1 hat is going to be beta 1 minus 0.5. Okay, so you will have a new beta 1, which like these two models are basically exactly the same. They are just observationally equivalent. And in econometrics, we just use this assumption. The expectation of e given x is equal to 0, which is a normalization assumption, but sometimes people call it like a strict exogeneity assumption. Okay, yeah, so that's the normalization assumption. So yeah, in statistics and in econometrics, we always have such problems. We can always have like multiple models that would generate the same dynamics of the process. And in our time series analysis, we will use, I think, a very crude way to do this. So we will choose the simplest model. Okay. Yeah, so you can think of this as a normalization, like the simplest model is a normalization, but this is just like the way that we typically use in time series. We will choose a simplest model. So I think I want to give you an example before we stop for today. Okay, an example of the redundancy. So suppose the first model that we consider is just a white noise process. So this xt is just equal to wt, and this wt is a white noise. So this is a white noise process. Okay. Now let's multiply 1 minus, say, let's 0.9b on both sides. Okay, then what you would got? So it's 1 minus 0.9b xt equal to 1 minus 0.9b wt. And this is xt minus 0.9 xt minus 1, okay, equal to wt minus 0.9 wt minus 1. So that is xt equal to 0.9 xt minus 1 plus wt minus 0.9 wt minus 1. Okay, so what's this? This is an ARMA 1.1 model. So we have a white noise process, which means xt is independent with xt minus s for all s. Okay, so xt is independent with all other observations. And we find that this is actually equivalent to ARMA 1.1. And actually you can show this is equivalent to any ARMA KK. And that means xt is what? xt is related to all xt minus s for all s. This is independent. This is fully related. Very, very different results, right? We can see the parameter redundancy actually creates a lot of problem for us. Okay, we know suppose the white noise process is a true process. So we know that our process, the xt, is independent with all other observations. But you can have a model such that the xt are related to all other observations. Okay, so again, so as I said, this is very wrong, and we need to pick the correct model. And in our analysis, we will pick the simplest model, so which is a model that this xt follows a white noise. Okay, so that's the example I give. So next time I will talk a little bit more about this parameter redundancy and basically to tell you how to use R to detect whether your model has the parameter redundancy. And then I think we will move on to some ACF plots and the PACF plots of the ARMA model. Okay, so I will see you on Wednesday. So thank you.